Hey everybody, and welcome to Calculus BC. In today's episode, we're going to be reviewing volumes from Calculus AB. And so I want to start off with just a graph of a standard kind of, any function. Well, let's call it y equals f of x. And I'm going to go and try and rotate this thing about the x-axis on some interval from a to b. So how do I do that? Well, if I rotate this shape, hopefully what I would get is I would get a mirror image, and I'll try and draw this as best I can, a mirror image on the other side, and it would end up becoming a volumed figure that had some type of cylindrical or smooth, rounded kind of texture to it. And the way this is achieved is it's achieved through integration. And what we learned last year in Calculus AB was that if we integrated a function on a particular interval and rotated it, we would get a volume. And so I want you guys to recall that what happens when we integrate is what we're doing is we're creating a bunch of small little rectangles, really infinitely thin ones. But for purposes of this, I'm going to draw kind of a thick rectangle. That way we can see what's actually happening here. And so from here, this thick rectangle, which is supposed to represent an infinitely small rectangle, this can be seen as the thing that's being rotated, which will eventually create these white curved figures here. And so what this blue rectangle represents is it represents what we call the radius of a disk. And the reason why that's important is because when I rotate and spin a rectangle around, what I get is I get a cylinder. And as we can recall from integrated 2, the volume of a cylinder is V equals pi r squared h. So there's that r that I was just talking about, the radius of that disk. Now hopefully we can see that if I rotate this disk around, this rectangle around, I would get a cylinder that would look kind of like this, where this would be the outer rim of the cylinder. So how do I translate this basic formula into something that we can apply in calculus? Well, notice how on the interval from a to b, or any interval, the length of the radius is changing. It's taller here, but it's kind of shorter right here, and it's super, super short where that large rectangle is. And then as we approach b, it starts to get a little bit longer again. One might say that the radius of the cylinder is dictated by the height of the function. So let me go ahead and express my volume of a cylinder that way. I'm going to say V is equal to pi times, instead of r squared, I'm going to call him f of x sub I star. Now that notation is kind of weird. I will explain that in a second, but that's going to be squared because this part is the f of x sub I star is acting as my radius now for reasons we just talked about. And that's going to be times h. Well, this x sub I star, what that basically is trying to say is that depending on how many rectangles we have, this is the ith slice or rectangle. Right? So in other words, like it could be like the 9th slice or rectangle, the 10th slice or rectangle. But ultimately, I think you're going to see we're going to eventually kind of let our slices approach super small. That way we can have an infinitely many of them. Let's find out what this h is. Well, if we look at these cylinders almost with our head turned 90 degrees on our right shoulder, we might be able to see that this cylinder here is actually facing towards the right. And so that way, in that sense, its height is being determined by this horizontal motion right here. And so this horizontal motion, which I'm highlighting in orange, is a change in x, which is why the h in all the formulas that you see in textbooks often get replaced by this delta x, because that is the height of this sideways cylinder. Hopefully you guys can see that. And again, this pi is a constant, so we're not going to replace him with anything. And it's going to be times f of x sub I star squared times delta x. So again, really just pi r squared h, right? That's our volume. Now, this rectangle, as it approaches infinitely small, we're going to sum up all of them. Now, I don't know how many rectangles that is, but I do know that I'm going to sum them up from when I equals 1, in other words, the first iteration of rectangle, to n number of rectangles. I don't know what that n is. And I'm just going to sum up all those rectangles. Well, the basic tenet of integration is that as the rectangles get super small, your area underneath this curve is going to get more and more smooth. So imagine, if you will, actually I'm going to pause real quick and show you what I mean so that you don't have to imagine it. Imagine, if you will, this image right here. We all know who this guy is. This is our favorite plumber, Mario, right? And this is what Mario looked like when he was on the NES, Nintendo Entertainment System. And that was back when graphics were built in 8-bit. So obviously he's supposed to represent a person, but he doesn't look like a person. Where are his fingers? Look at his mustache. His mustache looks like a police, like a police baton, right? His eye is just a brown rectangle, right? That doesn't make any sense. But what happened as technology began to advance and get better was that, similar to how these rectangles are going to get infinitely smaller so that we can smoothly fit rectangles underneath this curve and get a smooth area, similar to how that happened, the number of pixels allowed in video games began getting more and more. And that is why today we see Mario more like this, because there are so many more pixels that his face is actually smooth. His mustache actually looks like a mustache, right? Well, how does this relate to what we're doing? Well, again, I'm going to start off with the summation from I equals 1 to n of pi f of x sub I star squared delta x. And what I'm going to do is I'm going to go ahead and allow these delta x's to get really close to 0. And when they do, this number of rectangles will approach infinity. Well, we have a tool for that, don't we? I'm going to say the limit as n goes to infinity. And again, the consequence of letting n go to infinity means delta x is going to approach 0, approach infinitesimally small. And what happens is that this expression here becomes a summation like an S. My interval is a to b because that's where I was originally taking this stuff from. The pi will stick around. The f of x sub I star will just become the regular function f of x being squared, and the delta x will get so small it'll become dx. Now, because that pi is a constant, I'm going to kick him out because, as you know by now, I'd rather have my constants outside of my integration, outside of my calculus if I can help it. And this is how we come to find volume on a function figure. So in a minute, I'm going to come back with some examples and we'll rock and roll. We'll see you in a bit. Here comes my first example here. It's going to be y equals the square root of x. I'm going to integrate this thing on the interval from 1 to 4, and it's going to be about the x-axis. Now, what I'm going to do is I'm going to establish that because I'm rotating this thing about the x-axis, this is a dx integral. And we want to make sure we're very clear about that. We don't want to do the wrong integral. Otherwise it's bad. So from here, I like to graph these things. Now, I don't necessarily rotate them, but I do like to get the image of what it is that I'm actually graphing. And I know that my limits of integration are from 1 to 4. And I just draw sometimes just one rectangle like this, and that's going to be my dx right there. And I know I'm going to be rotating him about here. And so I'm going to set up my limits of integration from 1 to 4. Pi's on the outside. My function is what determines the radial length. So I'm going to call this rad x squared dx. And now I'm going to go and integrate this thing. I'm going to get pi integral 1 to 4. The square and the square root cancel each other out. I get x dx. And if I wanted to, I could go and do them analytically. I could just say pi times x squared over 2 on the interval from 1 to 4. Because 2 is a constant, and you guys know me by now, I like to kick the constants out. I'm going to call him pi over 2, and I'm going to go and evaluate just the x portion. Less moving parts makes my life easier. So I'm going to call him 4 squared, right, because I plug in my upper limit of integration, minus 1 squared, which is my lower limit of integration. And ultimately, at the end of the day, I end up getting 16 minus 1, so 15 pi over 2. What did I just find? Well, I just found what happens when I rotate this thing this way and find this volume of whatever this little device is. It looks like a thing. Yeah. So that volume right there is 15 pi over 2 units, whatever those units may be. Hopefully that makes sense. All right. I'll go and do another example here. This time, I think I'm going to rotate it about a different axis. Let's do a y-axis rotation. So let's do the same function, y equals rad x. This time, I'm going to bound him off by y equals 2 and x equals 0. And now we're going to do a y-axis rotation. So again, what does this say to me? This says that I'm doing a dy integral. Now, before I even draw the picture, I have to know that because this is a dy integral, I have to change this function so that it's x equals y. Right now, it's y equals x. Got to change that. Otherwise, it's bad. X equals y squared. This is the function that I'm going to be integrating at some point. So we will go ahead and do that. Draw the picture. Again, I like to draw pictures. Now, just because I switched the x and y doesn't mean that the function somehow changed. It's still this guy right here. But I am going to draw y equals 2. I'll switch to a different color and do that. Y equals 2 and x equals 0. So, oops, darn it. X equals 0. Close enough. So from here, as I rotate him about this axis here, hopefully it makes sense that the image will get duplicated on the other side, and I'm duplicating that as best I can. Whoops. And so, there we go. That looks a little better, maybe. And what's happening is that this is now my rectangular length, and I'm rotating him around to get a cylinder. Okay, sorry, that cylinder looks hollow. It's not hollow. And so what I'm going to do is I'm going to have to integrate this thing. Well, remember, this is a dy integral. So what are my limits of integration? My limits of integration are going to come vertically. So 0 all the way up to, looks like 2 in this case. Okay? So from 0 to 2 are my limits of integration. And again, I knew this was 2 because this is y equals 2. Hopefully that makes sense. Pi's on the outside. My function, again, not rad x, right? It's going to be y squared dy. So again, pi r squared height. Little bit of integrated math here. Y to the 4th dy. And if I integrate this thing now, which I'm going to get y to the 5th over 5, don't forget about that pi, limits of integration from 0 to 2. So how do I evaluate this? Pi over 5 outside looks like it's going to be 2 to the 5th minus 0 to the 5th, which is going to be 32 minus 0. So that's going to be 32 pi over 5. Again, what is this? Well, that's the volume of all this madness right here. All this stuff right here produces a volume of 32 pi over 5. Hopefully we're doing okay. I'm going to clean up the board a little bit, and we're going to move on to a different kind of rotation. Give me a second. So up until now, we've dealt with two shapes that were affirmatively solid. Every time I rotated them, there was never a gap in the middle. But we know from Calc AB that's not always the case. Sometimes we end up in this situation where we're crossing two functions instead of a function and a line. And I'm going to rotate this thing about the x-axis. And I'm going to go and graph this thing first. Now, notice what I haven't given you in this example. I did not give you limits of integration. That means that it's probably going to be your job to find those limits of integration. So let's go ahead and color code these. Let's go and make them sky blue, and let's make them orange. So the orange function we know well. That's this guy, right? That's this guy. The sky blue function, the quadratic, is going to be this dude. I am hoping that finding the limits of integration are pretty obvious. You would set them equal to each other, and if you look really hard, you'll be able to tell it's 1, 1. So from here, since I'm rotating this thing about the x-axis, it's going to rotate this way, and hopefully it makes sense that what I'm going to get is a duplicate image on the other side that kind of looks like this. It almost looks like like wings of sorts, you know. And the result of this rotation is that the shape is actually going to be hollow. And we want to make sure we are very aware of the fact that this thing is hollow, because when it's hollow, that means that there's a gap in the figure, which means some subtraction is going to be involved. So how do we deal with this hollow shape? Well, what I like to do is I like to imagine that there's a guy along that stands along the axis of rotation. I call him my dentist. And the dentist always integrates the function that is furthest away from him, the furthest function away from him. So from the dentist's perspective, that looks like it's going to be rad x. That's the furthest thing away. So that's going to be the integral from 0 to 1. Again, limits of integration coming from the points of intersection, pi. And the rad x is going to get integrated first. And then what happens is that the dental assistant comes in from behind and says, whoa, back up, bucko. You can't drill in all of that tooth. All of this extra tooth right here that I just highlighted in red that I'm going to erase needs to get removed. So the dental assistant drills out the extra tooth or function that isn't being placed inside the person's mouth. And so that is going to be pi integral 0 to 1. Looks like the closer function to the dental assistant is going to be x squared. I apologize. That the dental assistant always integrates the thing closest to him. I forgot to mention that. But obviously, we're going to be removing that much function, which means I'm going to be subtracting the result of those two integrals. So how do I finish off this problem? So that's going to be pi integral. Now at this point, because the limits of integration are the same, I like to initially see them as separate, but when I go to evaluate it, I put them back together. So this is going to be x minus x to the fourth dx, and then from 0 to 1. So that's going to be pi, and then I'm going to get x squared over 2 minus x to the fifth over 5, and that's going to be evaluated on 0 to 1. So what's that going to be? That's going to be pi bracket 1/2 minus 1/5 minus 0, right? 0, because the 0 in for x's will make it all go away. So what you have is pi times, and if you want to get a common denominator, it would be 10. So over 10, so 5 over 10 minus 2 over 10. So that I'm looking at 3 pi over 10 as the volume of this figure that is hollow. So hopefully the hollow figure makes sense. Again, it's just outer function minus inner function, outer radius minus inner radius. I'll be back with the next example. Give me a second. So I want to end with off-axis rotations. And so an off-axis rotation is basically when you rotate the figure off the axis. So it's a pretty unimaginative term. But if I gave you y equals x cubed, y equals 1, and x equals 0, and bounded the x cubed by this function here, by these two lines, and I wanted you to rotate about the line y equals 1, hopefully this will make sense to you that I'm going to draw this figure. I'm going to draw the figure. Now from here, the x cubed, since I'm only looking in the first quadrant, hopefully it makes sense that I'm going to kind of only draw not the tail end of it, but just the upper end of it. Y equals 1 is going to be like this, and x equals 0 is going to be, again, down here. Now this time I'm rotating this way, all right, and I'm rotating off of the axis, right, so off of this line. So how do I do this? Well, again, it helps. I like to draw the dentist, and the dentist says, all right, what exactly am I going to be integrating? Well, he integrates the thing that's furthest away from him. So in this case, the curve is actually furthest away from him. The problem is that when we integrate, we naturally get the space between the line and the axis. The problem is he's getting too much, right? And so he doesn't want, well, this whole space right here, well, that's going to be 1, right? That's going to be 1. But what we don't want, and the dental assistant's not going to play a role in this one, but what we don't want is we don't want this part here. This part here is the space underneath the x cubed. So the way I interact these guys is I do literally subtract them. And I subtract them together because I'm not creating a hollow figure. It's a solid figure, right? And that's the most important thing about this, is that this thing is solid. So there's not going to be two integrals being subtracted. So make sure you keep that in mind. From here, it's going to be integral from my limits of integration look like they're going to be from 0 to 1. And it's going to be pi and then dx here. Again, this is a dx integral. Why is it a dx integral, even though I'm rotating about y equals 1? Is because this line y equals 1 is parallel to the x-axis. That's why this thing is going to be a dx integral. So at this point, a little bit of integrated math. It's going to be 1 minus 2x cubed plus x to the 6th after I multiply this guy out. And I have not done any calculus yet. And that's going to be a dx right there. So that's going to be x minus, let's see, x to the 4th over 4, but then with the 2 here is going to be 1/2, and then plus x to the 7th over 7. And don't forget about that pi. This is all being evaluated on 0 to 1. So from here, we'll just evaluate it. So pi 1 minus, now if I plug in a 1, nothing changes. So it'll be 1 minus 1/2 minus, plus 1/7. Minus, if I plug in zeros for all of this, it's going to be 0, so thank goodness. So what is all of this? My common denominator is going to be 14. So I'm looking at 14 over 14 minus 7 over 14 plus, looks like 2 over 14. So that's going to be 7 over 14 plus 2 over 14. So 9 over 14, but don't forget about that guy. It's 9 pi over 14. Hopefully that makes sense. Let's do one when it's dy and when it's off axis and creates a hollow shape as our last example. So y equals e to the x, y equals 1, x equals 2. I'm going to rotate this thing about x equals 4. So always, a picture is worth 1,000 words. So please draw a picture of this figure here. Y equals e to the x is going to be an exponential function, so it'll look like that, more or less. Y equals 1 is going to cross this thing right here at the y-intercept because the exponential function has a y-intercept of 1. That's y equals 1. X equals 2, I'll just kind of guesstimate where that guy is. So this is x equals 2. And I'm rotating this thing. I'm going to draw this thing in yellow. I'm rotating this thing about x equals 4. This is my axis of rotation right here. So hopefully it makes sense that this thing is going to be hollow. There's all this gap here that I'm not going to be getting. So it's a hollow space. So I got to make sure that I know this. This is hollow. And it's dy, which means this guy's a problem. So how do I convert him into a y function? I take the ln of both sides. So ln of y equals ln of e to the x. The x comes down. Ln of y equals x times ln of e. Ln of e is 1. So x equals ln of y. And this is the function I'm going to be integrating. I want to get some limits of integration right here because this is the space I'm going to be rotating here. So what's my limits of integration? What are my limits of integration? Well, I know my lower limit of integration is going to be 1, and my upper limit of integration is going to be up here. Well, what happens when x equals 2? What does y equal when x equals 2? Well, I can plug that into there, right, into the original function and get e squared as my upper limit of integration. So I can go ahead and set this up right now. And I know it's going to be hollow, so it's going to be an outer radius minus an inner radius. So what I'm going to do here is I'm going to go ahead and draw my dentist. My dentist always sits at the axis of rotation. Whoops. I'm going to go ahead and put him down a little lower. And in this case, the axis of rotation here, what's furthest away from the dentist is actually 4, right? So my limits of integration or my integral is going to go from 1 to e squared pi, and that's going to be 4. But I don't want this nonsense right here. So it's going to be actually 4 minus the space that I just cut off. So that's going to be 4 minus ln y, and that's going to be squared dy. That's how I get all of this tooth in here that I'm highlighting in green. I got all this tooth that I'm going to be inserting in. Well, again, it's a hollow figure. The dental assistant needs to come in and save the day. And he says, wait, back up, dude. We don't want this much space. This red part is what we don't want. So what I'm going to do is I'm going to integrate the closest thing to me, which is the 2. But technically, the dental assistant has to get all of this space, which is 4, but subtract the 2. So I'm going to put that in as an integral quite literally. The integral from 1 to e squared of 4 minus 2 squared dy. Don't forget about that pi out there. And these guys are being subtracted. And at this point, this integral is not going to be solvable by hand for us. So what we would do is we would put it into a calculator, and we'd get an answer. And I apologize for having to pause. I actually had to upload the Inspire software onto the computer. And so here we go. We're going to calculate this thing. So what I'm going to do is I'm going to go ahead and do pi. So trig. Oops, darn it, wrong option. It's been a while. A little rusty. Sorry, the computer froze there. Interesting. Okay, so pi times shift plus is your short hotkey for an integral. So that's going to be from 1 to e squared. So that's going to be e to the second power. And I'm actually going to put it in individually. So that's going to be 4 minus ln of, and I put in as x, and it doesn't matter which one you put it in as because it's a variable is a variable according to this calculator, which I think is appropriate, dx. And then I'm going to say minus, right, that same deal here, so pi, shift plus, integral, so 1 to e squared, and that's going to be, looks like 4 minus 2, so I'm just going to go and put in a 2 squared, so 2, I'm not going to take any chances here, 2 squared dx, and I'm going to cross my fingers, I'm going to hit enter, and I got something kind of weird. Now, if I wanted a decimal, what I would do is I would go back up and I would hit this enter, and I would hit control enter for approximation, and it ends up being 70.165. So I'll write that down in our thing, 70.165, 70.165, and that ends up being the volume of this mass here being rotated about the line x equals 4. So hopefully that makes sense. As always, I would like you guys, if you watch the video, to please leave a comment in the comments area if you have a question about this lesson, or just have this question ready for class tomorrow. So if you want to, go ahead and do any one of those 3 things. But I will see you all in the next episode.